All right, here's chapter 21 problem. We're only going to cover problems 1, 2, 3, 4, and 7. All right, so problem 1, let me read it. It says, a certain telescope can just detect the sun at a distance of 10,000 parsecs. What is the apparent magnitude of the sun at this distance? For convenience, take the absolute magnitude of the sun to be 5. It's normally like it's like 4.8. So 5 is really close to 4.8. And then there's a part B. What is the maximum distance that the telescope can detect a nova that has a peak luminosity? So in the first part, we want to know what little m is. Right, so we'll call this part A, right? So little m, which is the apparent magnitude, and of course, in other words, we're going to use. Let me use the mouse here. We're going to use this equation where the distance in parsecs is 10 to the power of the apparent magnitude minus the absolute magnitude plus 5, and the whole thing divided by 5. All right, and so they give us that this is supposed to be m sub v, the absolute magnitude of the sun, as 5, and you can see how we could solve this. You just take the logarithm of both sides. We'll do it in just a second. So for part B, they say, what is the maximum distance? Okay, so we want to know d max, right? So that's an x. The maximum distance to detect a nova that has a luminosity, so the peak luminosity of 10 to the 5th solar luminosity, so 10 to the 5th times the luminosity of our sun. All right, so we need a separate equation for that one. All right, so let's get into this. All right, so I just took the given information. The distance is 10,000 parsecs. We want to solve for little m. They give us to use, and you can see why here. We use the absolute magnitude of the sun, of our sun, to be 5. So it's m minus m sub v, which is 5, plus 5. So minus 5 plus 5 obviously is 0. And so this simplifies to just 10 to the little m, which is what we're looking for, divided by 5. All right, so remember that's part of the exponent. Okay. All right, so this is actually pretty simple. You just take the logarithm of both sides, right? The logarithm of 10,000. Right. There's the logarithm of 10,000, and when you take the logarithm, where the base is 10, you just get what's in the exponent. So that's equal to little m over 5. Right, little m over 5, and so little m is just simply 5 times the log of 10,000. All right, and if you try that in your calculator, the log base 10 of 10,000 is 4, so 5 times 4, right, this is really 5 times 4. Because that's what the logarithm of 10,000 is 4. So it's the apparent magnitude would be 20. Right? So that's part A. All right. So what about part B? Okay. So what is the maximum distance that the telescope can detect a nova with a peak luminosity of 10 to the 5th solar luminosities? All right. So with that one, we've got to figure out what the absolute magnitude of a nova that peaks at 10 to the 5th solar luminosities. All right, so we'll figure that out now. Okay, so here's part B. Now the thing about part B is we have to figure out what the absolute magnitude of a nova that brightens up to 10 to the 5th times the luminosity of the sun. So this is the equation that we use. 5 here is, we normally would use 4.8, which is truly the magnitude of the sun, but since the absolute magnitude of the sun anyhow, since they told us to use 5 in the problem, so we're going to use 5. The 4.8 doesn't make that much of a difference. Anyhow, it's 5 minus 2.5 times the logarithm of L, which they give us as 10 to the 5th times the luminosity of the sun, and so the luminosity of the sun cancels down here, and so it's just 5 minus 2.5 times the logarithm of 10 to the 5th. So when you do that, you get a number about negative 0.053 is the absolute magnitude of the nova. Sorry, this is the absolute magnitude of the nova. All right, so this is for the nova. Nova. All right. So once we have that, now we can use that to figure out what. Remember, what are we looking for? So what is the maximum distance? So we need to use the distance equation again, right? So now since we know this thing, we can actually use the distance. What is the maximum distance at which the telescope can detect a nova having a peak? All right. So and you got to use the first part of this problem to figure this out. So it says a certain telescope can just detect the sun at a distance. Okay, so in the first part, it can barely detect basically an object that is has an apparent magnitude of 20. All right, so from the first part, our little m, lowercase m, which is the apparent magnitude, is going to be 20. That's what we have to use to solve this problem. And then our absolute magnitude is negative 0.05. All right, so let's solve this. All right, so we're finishing this up. This is problem, this is number 1B. So we're going to turn to this equation, of course. This is what we started with. The distance in parsecs is equal to 10 to the power of the quantity, in parentheses, the apparent magnitude minus the absolute magnitude plus 5 divided by, and the whole thing divided by 5. All right, so because this telescope can see the dimmest object that this telescope could see was told to us in the first part of the problem as a magnitude 20. So it's going to be 20 minus the absolute magnitude of this nova, which turned out to be negative 0.53. So it's minus a negative, so that's why we got a plus sign in here, plus 5, and then the whole thing divided by 5. So it's basically 10 to the 5.016. Anyhow, so that answer, of course, is in parsecs, so it's 102,470.8 roughly parsecs. That's how far away that particular telescope could detect a nova. Okay, so remember what a nova is. That's important to understand that. It's a white dwarf in a binary system where hydrogen accumulates on the surface. Well, it accumulates on the accretion disk, and then the material from the accretion disk falls onto the surface, and then there is this giant flash. In this particular case, this flash is 10 to the 5th times the luminosity of the sun. So we could see this thing, 100. So actually, hold on, let me see. So multiply that times 3.26. So this would be 300,034, roughly 300,000 light years away. So approximately 334,000 roughly light years away. Okay, so that would be, for example, there's a nearby galaxy that's actually in orbit around us. So this is they're called the large and small clouds of Magellan, and so this star would be in there. All right. Okay, let's do the next problem. Okay, so here's number 2. It says, repeat the previous calculation for a supernova that has a peak luminosity of 10 to the 10th times the luminosity of the sun. And again, we're going to use the absolute magnitude of the sun as 5. So for the supernova, we have to calculate the absolute magnitude. So since we know what the luminosity is compared to the sun, we can do that. It's a simple equation. You just say the absolute magnitude, which is capital M sub V of the supernova, is 5, which again, we're using this number that was given to us. It's normally 4.8, but we'll just use 5 for simplicity. Minus 2.5 times the log of the luminosity of the object. In this case, it's the supernova, right? So it's that divided by the luminosity of the sun, and of course, the luminosity of the sun cancels. So it's just so you just do this, and you're going to get negative. So this part of it gives you the negative 25, and then you subtract 5, then add 5 to it, and so the absolute magnitude of this supernova, okay, so it's for the supernova, would be negative 20. Remember what absolute magnitude is. It's what would it look like if this were 10 parsecs away, right? If it was 10 parsecs away, I mean, this would be just about almost as bright as our sun in the night sky. All right, so let's go on and finish this problem. Remember, we want to know what the apparent magnitude would be at a distance of, what was it? Let's see. So this would be at a distance of, let me write that down. So this would, what's the apparent magnitude at a distance of 10,000 megaparsecs? 10,000 megaparsecs. All right, which mega, of course, means times 10 to the 6th. All right, so here we go. All right, so we're going to use this equation. The distance is in parsecs is equal to 10 times the quantity. Once again, the apparent magnitude, which is the little m, minus the absolute magnitude plus 5, and then that whole thing divided by 5. So the whole thing is in parentheses, right? And all this whole thing is in. Sorry, this entire thing here is in the, that's part of the exponential. All right, so again, you do the same thing that we did before. You take the logarithm of both sides, and so, so all this stuff, this would be divided by 5. This whole thing over here would be divided by 5, so I brought the 5 over to the other side. So it'd be the log of 10,000 times 10 to the 6, right, because they told us it's megaparsecs. All right, so when we do that, so that's actually pretty not too bad. Let me put this in my calculator. All right, so let's finish this problem. So remember, the distance they give us is 10,000 megaparsecs. So it's going to be this 5 comes over to the other side. It's going to be log 5 times the log of 10,000 times 10 to the 6, which turns that whole thing, the log of 10,000 times 10 to the 6, is just 10. Right, so 5 times 10 is 50, and that's equal to little m, which is the apparent magnitude. That's really what we're looking for, minus a negative 20, right? Because that's the absolute magnitude of a something, a supernova that had a luminosity of 10 to the 10th times the luminosity of the sun, plus 5, and that plus 5 that's normally part of the problem. It has nothing to do with the magnitude of the sun. All right, anyhow, when you do that, you get 50 equals little m plus 25, and so you subtract 25 from both sides, and then you get that little m is it has an apparent magnitude. So that's the apparent magnitude of this supernova, which is this. You're talking about something that is extremely far away. This is 10,000 megaparsecs, right? That's bigger than the known universe, which So anyhow, if this supernova would occur, the observable universe, I guess I should say, we can see a distance of about 13 billion light years in any direction. So this would be, This would be a lot more than that. This would be something like 32 billion light years away.